Next, we are going to see the impulse invariance method. So, impulse invariance approach is used to design discrete time IIR filters by transforming a continuous time filter into a discrete filter meeting prescribed specification. In impulse invariance method, the IIR filter is designed such that the unit impulse response h of n of a digital filter is the sampled version of the impulse response of an analog filter. Let h a of s is a system function of analog filter. This can be expressed in partial fraction form as h a of s is equal to summation of k is equal to 1 to n c k divided by s minus p suffix k. So this is S-plane to Z-plane transformation. So this is the imaginary axis of your S-plane. So the when mapping to the Z-plane, it is coming as a unit circle, and the left half of the S-plane, so it is coming on the points on the circle, unit circle. Now consider the poles on the left half of S-plane where sigma is less than 0. These poles map inside the unit circle. So all the S-plane poles in the negative real axis part of the negative real parts map to the Z-plane poles inside the unit circle. So stable analog poles are mapped into stable digital poles. So unstable poles are mapped outside the unit circle. So impulse invariant method is not one-to-one mapping, rather than it is many-to-one mapping. So since it is many-to-one mapping, here there is a when this filter is used for this high pass filter or band pass filter or band reject filter, there is a possibility of getting frequency aliasing. So this impulse invariance method is a many-to-one mapping where many points in the S-plane are mapped to a single point in the Z-plane. Okay, this diagram shows the Z-plane is S-plane to Z-plane mapping. So this is a many-to-one mapping. So the digital filter transfer function is given by h of z is equal to summation of k is equal to 1 to n t c k divided by 1 minus e to the power p k t z inverse. The impulse invariant method is appropriate for designing the low pass and band pass filters only. The impulse invariance method is unsuccessful for implementing digital filters such as high pass filter and band reject filters. So next one is we are going to see the steps to design a digital filter using impulse invariant methods. So from the given specification, find HA of S. What is HA of S? That is an analog system function, okay, or the transfer function of analog filter. Select the sampling rate of the digital filter, t seconds per sample. Express the analog filter transfer function as a sum of single pole filters. So already we have seen the analog transfer function HA of S can be represented as k is summation of k is equal to 1 to n ck divided by s minus pk. Compute that Z transform of the digital filter by using the formula h of z is equal to summation of k is equal to 1 to n ck divided by 1 minus e to the power pk t into z inverse. For high sampling rates, h of z is equal to summation of k is equal to 1 to n t ck divided by 1 minus e to the power pk t into z inverse. So now we are going to see one problem on impulse invariance method. So the problem is for the analog transfer function h of s is equal to 2 divided by s plus 2 into s plus 1 into s plus 2. Determine h of z using impulse invariance method. Assume that time t is equal to 1 seconds. So now we are going for the solution. First, you write the given transfer function. H of s is equal to 2 divided by s plus 1 into s plus 2. Now we are going to write this analog transfer function in partial fraction form. So a divided by s plus 1 plus b divided by s plus 2. Now we have to find the value of a and b. We have to find the value of a and b. So what is a? A is nothing but h of s into s plus 1 at s is equal to minus 1. What is a? How we will get the value of a? H of s into s plus 1 at s is equal to minus 1. Similarly, how you will get the value of b? H of s into s plus 2 at s is equal to minus 2. So while substituting this in h of s, you will be getting the value of a and b. So here we are getting the value of a as 2 and the value of b as minus 2. So while substituting, we are getting 2 divided by s minus minus 1. So it will become s plus 1, and this is nothing but 2 divided by s minus minus 2. So we know that h of s can be written as summation of k is equal to 1 to n ck divided by s minus pk, and h of z is equal to summation of k is equal to 1 to n ck divided by 1 minus e to the power pk t into z inverse. So s minus pk is transferred to 1 minus e to the power pk t z inverse. So here we are having two poles. One is minus 1 and one is minus 2. So in the place of p, you are putting minus 1 and minus 2. And t, you have taken the question, we have taken it as 1 seconds. So you are getting as 2 divided by 1 minus e to the power minus 1 into z inverse minus 2 divided by 1 minus e to the power minus 2 into z inverse. By using your calculators, you find the value of e to the power minus 1 and e to the power minus 2 and substitute in this expression. So after substituting in this expression, you will be getting 2 divided by 1 minus 0.678 into z inverse minus 2 divided by 1 minus 0.1353 into z inverse. Okay. So after subtracting these two, you'll be getting h of z is equal to 0.465 z inverse divided by 1 minus 0.503 z inverse plus 0.04976 into z to the power minus 2. This is the answer what you are getting.